When you admire a Mediterranean seascape, everything seems as peaceful as a huge mass of water, whose surface is sometimes moved by the wind. However, this is not necessarily the case. In order to try to discover underwater realities, it is necessary to start by observing them using conventional scientific oceanographic measurements. At the end of the 1960s, the subject of marine pollution became more and more prominent in the news, and my excellent colleague and friend Jacques Picard, the famous deep-sea explorer, and myself were consulted to study the possibilities of mitigating the effects of this pollution. Here we are, for example, welcomed in Sardinia by the local authorities. Considered part of the vast network of underwater currents in the Mediterranean, Sardinia is bordered by water which, during its long journey, has collected all kinds of polluting products, particularly along the nearby Italian coast. At various points along the coast, we started by collecting the different plankton species with a very fine mesh net. We identified them and counted them under a microscope. We observed the daily variations of the transparency of the surface water. We measured the water temperature, salinity, oxygen and carbon dioxide content as a function of depth and time. We have taken many samples of this water for laboratory analysis. In particular, samples taken at the level of the seabed to highlight the exchanges between bottom sediments and the water. Nothing is permanent. But to understand all the phenomena that are currently causing public concern, it is necessary to observe the Mediterranean as a whole. And it is in the Strait of Gibraltar, 15 kilometres wide, 300 metres deep, that the variations of the underwater balances manifest themselves in the most spectacular way. Indeed, our Mediterranean, or Mediterrnean in Latin, is a vast basin of evaporation. It is so active that the rains on its large rivers, the Rhone, the Danube, the Nile, etc., do not anywhere near compensate for the enormous evaporation on its surface. It is estimated that the loss of its water level by simple evaporation is 50 centimetres to 1 metre per year. And it is obviously through Gibraltar that water from the Atlantic can compensate for this loss. However, these quantities are often considerable, sometimes more than 1 million cubic metres per second. Variable, it is true, with Atlantic tides, seasons and depth. Generally speaking, the more water evaporates in the Mediterranean, the more the Gibraltar Gap opens. But what evaporates is distilled water. So what remains below the surface is richer in salt, colder and heavier. It therefore tends to sink, accumulate at depth and eventually partially return to the depths of the Atlantic in the form of cold underwater river through the bottom of the Strait of Gibraltar, especially when the Atlantic tide is low. Of course, many other natural phenomena also influence this general trend. There is the alternation of hot and cold seasons. For example, the surface water heated by the summer sun expands, lightens and evaporates. The remaining water is slightly heavier due to the increase in its salt content. It flows by causing mixtures over the first few metres of depth. Below about 10 metres, scuba divers know from experience that the water cools quickly. When the press comments on sea level rise, it is curious that it never refers to the masses of sediment torn from the surface of continents by erosion and then dumped into the water by rivers and waves. Neither the still poorly known underwater volcanic activity nor the slow and uncontrolled drift of the continents. If global warming does cause general expansion, it represents little, but given the immense surface area of the Mediterranean, it is sufficient to sometimes animate the cold underwater river in Gibraltar when the Atlantic tide is low. On the other hand, prevailing winds such as the Mistral, Tramontane or Levante raise slightly breaking waves that cream the warm surface water, push it and accumulate it in the direction in which they blow at a speed of a few dozen centimetres per second. Swimmers know that the water temperature at their favourite beach varies greatly with the wind direction. Naturally, the relief of the bottom and the contour of the coast also have significant influence on the underwater currents. They divert, weaken, or accelerate them locally. As a result of the rotation of our planet on itself, all underwater currents undergo a force perpendicular to their displacement. It is the strength of Coriolis. In the northern hemisphere, this force tends to deflect these currents to their right. All these elements are the active drivers of currents in the Mediterranean as elsewhere. But if they are easy to list, it is much more difficult to synthesize them in order to deduce a general representation. This requires many direct measurements repeated over long periods of time and over large areas. The observations made by the tireless satellites and their infrared viewpoint help to alleviate some of these difficulties, which are inherent to all scientific oceanography. Inside all of these bodies of water, in constant motion, there is life, a lot of life, a cruel and anguished life because it feeds itself by eating itself. Its forms are extremely varied. This ranges from the tiny but largely dominant phytoplankton to large marine mammals. Phytoplankton absorb dissolved CO2, conserve carbon, and release more than 1/3 of the oxygen we breathe. The Mediterranean is characterized by its exceptional biological diversity. It occupies only 1% of the world's ocean surface and supports 28% of living species which are not found anywhere else. For several decades now, this Mediterranean fauna has been enriched in an unexpected way. The opening of the Suez Canal in 1869 opened a water passage from the Red Sea to the Mediterranean. Fortunately, the route of this canal passes through the bitter lakes, which are hypersaline. That's where the boats meet. Due to their salinity, these lakes have long been a barrier to the passage of wildlife between the two seas. But the mixing caused by the constant passage of large ships has reduced their salinity, and their role as a biological barrier has diminished. As a result, some Red Sea animals have been able to migrate to the more nutrient-rich Mediterranean. Here are some of the most spectacular examples. Today, nearly 300 species originating from the Red Sea have been identified in the Mediterranean. One can anticipate that the modernization of the canal will further increase this invasion. I hesitate to mention it here, but there may come the day when Red Sea sharks could perhaps cross the canal. To raise another area of public concern, it should be noted here that the water of the world's oceans contains about 40 trillion tons of carbon, 50 times more than the atmosphere we breathe. CO2 absorption from the air occurs on the surface of the water, especially when it is agitated by waves. In winter, the surface water is cooled. Its ability to dissolve CO2 is increased, especially as the solubility of this gas also increases with its cooling. This is due to their physical characteristics. Once dissolved, carbon is absorbed by phytoplankton, which is a plant and, like all animals, lives from photosynthesis. Basically, It breathes dissolved CO2, conserves carbon to grow, and releases oxygen that escapes into the water and then into the air. Then, this phytoplankton is used as food for zooplankton and all that lives in the water. As they die, all this biological mass flows and accumulates on the seabed. There it mixes with the sediments for very long periods of time. In time, and by biochemical reactions too complicated to be described quickly, it is gradually transformed into limestone, CaCO3, and eventually into hydrocarbons, our dear oil. The public is also concerned about the alleged acidification of seawater, and yet, although repeated nearly everywhere, this statement is false. Acidity is easily measured in pH, or hydrogen potential. Anything below 7 pH is acidic. Everything above is alkaline. However, the average pH of Mediterranean water, like that of all oceans, is 8.2, varying between 7.6 and 8.5. So seawater is not acidic, it's alkaline. In addition, this alkalinity tends to increase with evaporation, and therefore with possible global warming, quite the opposite of what is told to the public. At the end of my career as a scientific naturalist, I witnessed with astonishment a curious confrontation of contradictory opinions on the subjects of ecology and climatology. A chaos of antagonistic statements made by people who are often very competent but who consider each other with anger and contempt. Out of their convictions, they often do not tolerate doubts or discussions. However, these are extremely complicated and new subjects that are still poorly understood. Watch them argue, condemn, exclude each other. They count each other, compare the number of their supporters, and often consider these figures as arguments with scientific value. My generation has worked in a world of researchers with less unshakable convictions. The various opinions could still be discussed freely in order to try to understand the result of observations about nature that sometimes seemed contradictory in appearance. That is why it seems to me that the time has not yet come to conclude on these subjects of climatology and ecology. Again, these are still very young, very complex sciences, and no one really understands them. Let's wait a few years before suggesting any solutions to the public who fortunately still trust us. It is too serious and still too uncertain to predict the future with anywhere near complete certainty.